This is a computer. Computer works by performing calculation using a binary code. And binary code, well, it is just a series of zeros and ones. Each 0 and 1 is called a bit, and a bit in the computer is just a switch that can be either on or off, where on represents 1 and off represents 0. And these switches, when placed in a different circuit, makes up a logic gate. You may have seen these logic gates before. It still blows my mind, but everything we do on the computer is just a binary code that is run through the logic gate to give out useful information. Remember this, data is unprocessed zeros and ones, which may not be that useful. However, information is processed data that is meaningful and useful for the users. If you still can't understand this, in cooking terms, data are the raw ingredient and the information is a cooked dish. Let's move up to networking portion first. Any device on the network is called a node, and these nodes have a network interface card built in them, which allows them to connect with other devices. Remember, all network interface cards have a unique address known as a MAC address, and this port you see, this is an Ethernet port. You can use an Ethernet cable to connect two PCs directly and form a peer-to-peer connection. Now, if you replace a PC with some server, that would be a client-server architecture. The server serves the content, and the content depends on the type of the server. A web server shows the web pages. A mail server handles email. The FTP server allows sharing of files. A DNS server resolves domain name to the IP addresses, and the list can go on and on. But let's take a moment to understand different modes of communication first. A simplex mode is where information is transferred in only one direction. An example is a TV broadcasting system. A system can broadcast content to the viewers, but the viewer cannot send any data back. In HowToNetwork, data can be sent or received in both directions, however, not at the same time. A walkie-talkie is the best example, where both persons can talk but only one at a time. And full duplex is where our data can be sent or received in any direction simultaneously. Our network topology is the full duplex. When connected, devices can share information in the form of packets. And to transfer these packets, there are many protocols involved. We use TCP/IP model, which is based on the OSI model. For now, just remember, protocol is a set of rules that every device on the network must follow. We'll dive into it later on in this video. To connect multiple nodes using a cable, we can use a hub or a switch. Since hubs are outdated, we are going to use a switch. A switch remembers the MAC address of the connected devices. It stores this information in the MAC table and forwards the packet based on this information. And this group of interconnected devices is called a network. This one is a local area network. If it connects multiple LANs, then it's a MAN network. And if it connects multiple MANs, that makes it a WAN. The name is given on the basis of size of a network. Devices within a network can share the information, but only if they have an IP address. An IP address, it is an identifier for the devices on the network. There are two versions, IPv4 and IPv6. This is what they look like. Remember, IP address is also a binary number, and it is 32 bits long. And since a bit can have only two combinations, and there are a total of 32 bits, we can make up to 2 to the power 32 combinations, which is 4.3 billion addresses, which is not as sufficient. So we use a private IP address inside the local network and assign a unique public IP to our routers. But don't be confused, router has at least two interfaces, one facing the internet side with a private IP address, and it acts as a default gateway for the nodes, and another one facing toward the internet, which has a public IP configured. And when a packet is destined for the internet, the router does a network address translation, or a NAT, which replaces private IP with a public IP address when the packet leaves, and vice versa when it receives the packet. It uses a mapping table to keep track of all these NAT records. We know that devices need an IP address to communicate, and we can configure it manually, and that would be called a static IP since it does not change. Or the DHCP server can hand out all the network configurations automatically. Such configuration is called a dynamic IP allocation, which is often used in most networks. Now, since our devices are fully configured, they can communicate and share the resources. Sharing resources means making something available to all devices on the network. For example, a printer can be used by any computer on the network, which is a type of resources sharing. Let's see how a PC communicates in a LAN network. Let's imagine PC A wants to send a packet for the PC B. It sends that packet to the switch, and if you remember, switches work on the layer 2 of OSI model, which means it forwards the packet based on the MAC address, not the IP address. And initially, switch has no idea what is the MAC address of PCB. So it sends out a ARP broadcast to all the devices, and PCB responds back with the MAC address. Switch updates its MAC table and forwards the packet. Here, when the switch sent out the ARP packet to all the connected PCs, that was a broadcast transmission. And when PCB replied, that was a unicast. Similarly, when a packet is sent out to multiple nodes, that is called a multicast. So this is how data transmission takes place in a LAN. However, things get complicated when a device wants to send a packet for the IP that is not in our network. Such packets are sent to the default gateway, which is our router. A router can route traffic between different networks, heck, even multiple networks. Router performs routing based on the pre-configured routes, and these routes can either be configured manually, which is called as a static route, or can be configured automatically using dynamic routing protocols. And there is also a default route. If none of the existing route matches the packet destination IP, it is sent to the default route. And if you look into the dynamic routing protocols, there are two major types. Interior gateway protocol, which is used to route within the autonomous system, and exterior gateway protocol, which can route between the autonomous system. Let's look at this chart. Under the IGP, there is a subtype, link state, distance vector, and the hybrid protocols. And under the EGP, there is a path vector protocol known as BGP or border gateway protocol. These are the examples of corresponding IGP protocols: OSPF, ISIS, RIP, which has two versions, IGRP and EIGRP. Each of these protocols work in their unique way. If you want to learn more about the routing types, I've already made a video on this. So much on the protocols, but how do a packet actually get routed? Let's assume PCA wants to send a packet for the PCB. Using the subnet marks, PCA knows that the PCB is not on the local network. So the packet should be forwarded to the default gateway. And routers also have a unique MAC address for each of the interfaces. So the packet has a destination MAC address of the default gateway. So just look at the destination MAC address and forward it to the router. Router checks its routing table and find out that the destination IP is a part of directly connected network, which is 172.18.10.0. So the router looks up the ARP cache and searches for the MAC address of the PCB. If the MAC address is not found, it sends out an ARP request to discover it. The PCB responds back, and now router updates the destination MAC address and sends out the packet. Switch then looks up the destination MAC and forwards that packet to the PCB. This is how a packet gets transferred. Now during the transmission, the packet goes through different layers of protocol. These layers can be represented using a model called the OSI model. However, in practice, we often use a simpler model called as TCP/IP because it combines the feature of OSI into fewer layers. The data originates from the application layer. It is then processed, which involves encoding, compressing, and encrypting. Once ready, data is broken down into multiple segments at the transport layer. At this point, they can either use the TCP or the UDP for the transmission. TCP is the reliable one, but slow. On the other hand, UDP is reckless, but fast. Both have their own pros and cons. See this infographic to better understand their differences. Now these segments have to be sent to the remote destination. So IP header is added in the network layer, which include information such as source IP, destination IP, time to leave value, etc. The packets are now encapsulated into frames. At this layer, layer 2 information such as MAC address is added to the frame. And since everything is ready to be sent, the frame is then converted into electrical impulses where it could be sent through the Ethernet wire. Or frames can be converted into light pulses if you are using a fiber optic medium. Now let's break down some of the network performance metrics. Latency, it's the amount of time it takes for the packet to reach from the source to the destination. You can check the latency using a ping command, which uses an ICMP protocol. Jitter is a variation in the value of latency. If you see packets being delivered at different intervals, that indicates jitter in the network. Higher jitter means unstable network. Bandwidth is the maximum amount of data a link can carry, while throughput is the actual amount of data that is transmitted by the link. And finally, packet loss is where the sent packet doesn't reach the receiver. Obviously, explaining the entire concept in just 100 terms is impossible. However, in this video, I focus on the fundamentals, and there is still a lot to cover. If you love this video, subscribe to the channel. I'll be dropping some bombs soon. Meanwhile, like and comment, and I'll see you in the next session.